So we've introduced the combinations of multisets. Actually, there are a lot of other forms of combinations. For instance, when occurring, we might want the number which are not adjacent. This kind of problems is called non-adjacent combination. Its definition is that we are picking R non-adjacent elements from set A, which contains n elements. The meaning of non-adjacent is that we couldn't choose adjacent numbers j and j plus 1 together. How should we explain this? Well, for example, we have 6 elements in total, and we want to choose 3 from them. How many non-adjacent combinations are there? It could be 1, 3, 5 or 2, 4, 6. 1, 2, 5 is not allowed because 1 and 2 are adjacent, which are not allowed by non-adjacent limitation. So how many combinations are there? We got a little bit experience that we are doing combinations of multisets. We could use index number. So could we do something similar for non-adjacent combinations? Well, for example, we have such a non-adjacent combination 1, 3, 5, 7, 9. What are the index numbers? The first one is 0. What about the last one? There are 5 numbers. The last index is 4. How should we manipulate the non-adjacent limitation in order to construct a corresponding combination without repetition? We know that what does non-adjacent combination means? It means that the index number increased at least by 1. Or the difference is at least 1. If we subtract the indexes from the numbers, could we construct a new combination? Let's try. In non-adjacent combination 1, 3, 5, 7, 9, we subtract the index number from each element, and we get such a new sequence. 1, 3, 5, 7, 9 becomes 1, 2, 3, 4, 5. It seems that we get a new sequence, and we would discover that the new sequence still seems to be a combination. We also want to know whether it's a combination without repetition. Let's look back. In such a sequence, for instance, let's make it more generally. We want to pick R element from n1 elements. How many arrangements are there? And first we pick the R non-adjacent elements and denote them by B1, B2 until BR. Their index are 0, 1, 2 until R-1. According to the previous analysis, we want to subtract the indexes from the numbers. So we construct a new sequence which is B1, B2 minus 1 until the last number is BR minus its index. It's BR minus R minus 1. How many numbers are there in this new sequence? Of course, there are also R numbers. As the original non-adjacent combination is an ascending sequence, so 1 till B1, Bn less than n. Now we will think that, so what's the maximum value in the new sequence? The largest possible number is BR minus R plus 1. BR is no greater than n. So now we construct a sequence whose maximum value is n minus R plus 1. What about the minimum number? Obviously, it should be B1, which is 1. So the range of R numbers is from 1 to n minus R plus 1. Are all elements in sequence different with each other? Let's take a look at C1 and C2. We know that if C1 equal to B1, C2 equal to B2 minus 1, C1 and C2 are not adjacent. The difference between B1 and B2 is larger or equal to 2. So as C1 equal to B1, C2 equal to B2 minus 1. C2 is at least larger than C1 by 1. And so forth. We could prove that for sequence C, C1 less than C2, C2 less than 3 until CR. So by subtracting the index number, we've constructed a R element ascending sequence in the range from 1 to n minus R plus 1. So actually, non-adjacent combination is corresponding to C n minus R plus 1 R. For the detailed proof, we could use the bijection method to give the corresponding sequence. Here, we will skip it. There are many different meanings of combinations. Next, let's look at the problem. We all know that a key application of combination is to increase the security. No matter how complex your password is, no matter how solid your lock is, there is an important problem that who should open the lock? If we only give the lock to one person, if there's any problem, the security couldn't be guaranteed. In order to make it more secure, we usually need to use combinations to ensure the security. Let's see this example. In a secret institution, there is a secure lock. How should they guarantee the security? Therefore, they design a system. In this system, one needs to use multiple keys together to open the lock. How should they distribute the keys? There are 7 key members in this institution. It's too hard to all 7 people together. So if 4 of them are together, they could open the lock. The problem is that in such a complex mechanism, how many different locks should they have? And the keys are distributed to different persons. How many keys should one hold? The problem seems to be extremely complex, but let's analyze it carefully. 4 members must gather up. This means that any 3 persons among the 7 persons would be in lack of a key, in lack of at least one key. And the one they lack must not be the same. If they lack the same key, it's possible that 4 of them could lack the same one. This means that any combination of 3 members are corresponding to a unique key. So how many keys should they have? It means that among the 7 members, any 3 is corresponding to a new key. So how many different keys are required? The answer is C73. For the second problem, the problem is that how many keys should one person hold at least? This time, we think that anyone are responsible that any other 3 persons would lack keys, and the lacked key should be held by me. This means that for every other 3 persons, we should have a key to be corresponding to them. Where are the people from? It's from the other 6 members except myself. This means that for every 3 combination of 6, one key is held by me. So how many keys should I have? It's actually C63. Only if I have such many keys, I could guarantee that with any 3 members among the 6, I could open the lock. So although this problem seemed to be very complex, with careful analysis, we could get an easy combinatorial model. We just introduced different kinds of permutations and combinations. Now let's sum up. The most fundamental permutations and combination are permutation without repetition and combination without repetition. The corresponding model is a ball model. For example, we pick R balls from N. If we care the order, it's permutation without repetition. If we don't care the order, it's corresponding the combination without repetition. As for the number of permutation is P and R. The number of combination is C and R. In addition, we might consider some repeated elements. We introduced permutations with repetitions and combination with multisets. Combination of multisets is as a fruit composed made with pears, oranges, and apples. As is a combination, we don't care the order. But here, repetitions are allowed. So we know that by analysis, we find out that there are Cn plus R minus 1 R arrangement for picking R fruits from N categories. For permutations with repetitions, There are a typical example, which is English word. We use n letters to construct a R character string, and the order matters. Well, the characters are repeatable. For constructing such a R string with n letters, there are n choices for each slot, and we have R slots. So the number of permutation with repetition is n to the r's power. Finally, we have something called permutation of multisets. Here, we require multiple characters. For example, R1 A's, R2 B's. Finally, we need to construct an n string. And it's a permutation. We care the order. Meanwhile, there are repetitions. How should we analyze these problems? We found that for repeated elements, we want to divide it by redundancy ratio. Here, R1's means the redundancy ratio of A is R1's factorial. R2B's means that the redundancy ratio of B is R2 factorial. So the number of permutation of multiset is n factorial divided by R1 factorial, R2 factorial. Here we have two keywords with repetitions and multisets. What's the difference between them? Let's analyze it carefully. Actually, with repetitions means that the number of elements is unlimited. They are unlimited resource. For example, fruits like pears and apple, you could get as many as you want. But for multiset, the numbers of elements are limited. For instance, R1A's, R2B's. So with repetitions and multisets are corresponding to different things. Here, we've introduced a lot of permutations and combinations. Actually, there are just a few among all permutations and combinations. Hopefully, we could experience the art of permutations and combination by doing exercises.